So maybe that's actually a good thing to do. And let's bring in the duplicates, but after we learn the basics. So let me see here what I can do. Share a whiteboard, share. Okay. So now I got a whiteboard over here. Everybody see big white open space. Let's say that we wanted to have, do we have any kind of tools? I guess it's not tools. Let's just say, let's make up some numbers. Right, and I'm going to be writing with my left hand using the mouse.
Sorry, Mr. Barry. Sorry, I think we only see a white stripe in the screen. I'm not sure if that's just me.
If it's just a big white screen, that's probably good. This is the pencil. Oh, you don't see the whole screen?
It's mostly just black.
That's all, you don't see a big, interesting.
There we go.
There it is. Okay, so I have to put it on my main monitor. I didn't know that was the rule. Okay. All right, so now I have something hopefully that works here. So let me now erase this, eraser, erase many things. Okay, so let's say here that I'm going to make up some data and I'm going to write, we're just going to make up some numbers. 6, 2, 9, 11, 4, 16, 1, what numbers am I missing? 7, 3, there we go. So there are some numbers and we want to make a binary search tree out of those numbers. Let's say those numbers were coming at us one at a time and we are being asked to put them in a binary search tree. So let's say the first number that comes in is 6. So what do we do with that? I'm going to draw, right? So if the first thing that comes in, I don't want the text tool anymore, get me out of that. I want just a draw tool. There we go. All right. So if the first number that comes to me is a 6, I don't have any choice. That becomes the root, right? So 6 is my root. Okay, then what comes next? Comes to me next is a 2. So where does the 2 have to go?
On the left of the 6?
Has to go to the left. So I'm going to say, okay, here's the 2. Again, I apologize in advance. I'm drawing with my left hand and with the mouse, which are both, it's a bad combination. Okay, how about the 9?
On the right of the 6.
Has to go to the right. It's bigger than 6, so there's the 9. Okay, great. Now we get the 11. Where does it go? Somebody else.
To the right of 9.
Has to go, it's bigger than 6, it's bigger than 9, so it has to go to the right of 9. So here's my 11. Great. What's next? Now we get the 4. Somebody help me.
To the right of 2.
Okay, it's smaller than 6, but bigger than 2, so it has to go here. That's the 4. Okay, there's my 4. Okay, now we get 16. So where does that go?
All the way on the right.
Bigger than 6, bigger than 9, bigger than 11. It goes now down here. That's now 16. Great. All right, then we get 1. Less than 6, less than 2 seems to be that it has to go here. Then we get 7, right? So now somebody help me, where does 7 go?
Left of 9.
It's bigger than 6, but it's less than 7, so it becomes 7's left child. Thank you.
Couldn't it also go to the right of 4? Is there a reason we don't do that?
It can't because it's bigger than 6, so it can't go anywhere on the left side.
Oh, got it. Thank you.
Right?
Yeah.
It sounds like it could, but it can't, right? There's really only one place it can go. You have to start at the root and go, okay, it's bigger than 6, it's less than 9, so plop, there it goes. Okay. How about 3? Last one.
To the left of 4.
Less than 6, greater than 2, less than 4, it has to go down here. Okay, does that make sense? So we've created a binary search tree. We've put the numbers where they have to go to be a binary search tree, and kind of by accident, it's also height balanced. Do you notice that? Right? It's within 1. In fact, it's the same. The height is the same on the left and the right. So it's actually a height balanced tree. Okay, a height balanced binary search tree. Does that make sense? Now, just to follow up on the question that was asked, I think that was Bjorn maybe asking that. If not, sorry, it was somebody else. So now let's say that another 2 comes in. Gary, go ahead. Question, Gary? You're muted, so. Well, it doesn't have to be high or low, it's just how the tree forms. But certainly if we now put 2 more numbers down here that were bigger, that could be a problem. Or if we put several numbers that were less than 11, but there's not many numbers there. But yeah, and it can be anywhere in the tree, but if one branch starts to just get really long and lanky, then it can be out of balance. Right? Okay. All right. So now let's go put a duplicate. Now pick either left or right, right? Pick either left or right. You're going to see that the duplicates have a funny issue here, right? So let's say that we add another 2 to the list, right? So pick whichever one you want. So let's say, well, we decide for our algorithm that it's always going to be duplicates go to the left. So let's find a place for the 2. It's less than 6. Well, it is equal to 2, but we said 2, we go dupes on the left. So we know we need to go to the left, but now it's bigger than the 1. So guess where the second 2 ends up? It ends up down here. So yes, that's where it belongs, but do you see that we could end up with some sort of interesting issue? Do we really feel good about the fact that the dupes are being spread through the tree in various places? I don't know. It's a little bit problematic. It's going to still work when we learn about traversing the tree. We can still make them come back in order, but if you're searching for one, it's a little bit inconvenient that you don't really know when you're done searching, right? You can't really stop because you've got to cover everything to the left of the 2 node all the way down to see if there might be more 2s. So it doesn't feel ideal. It works, but it doesn't feel ideal. And in fact, we're going to solve that problem in our project by thinking outside the box and doing something different, right? But with a binary search tree, you pick left or you pick right for your algorithm, and then you just deal with the consequences later. Okay. All right. Any questions? Any follow-ups on that?
What would it look like if you were to add another 3? Because 3 is a leaf. Would it come off of a 3?
It would go here. Right. Now, it happened to be right next to the other 3, which was convenient, right? But it won't always be so, as we saw with the 2. If we add another 6, where's that going to go? It's going to go to the right of the 4, right? So here's the 6, right? So the numbers can start getting spread out through the tree. There's no guarantee that they end up together because the tree doesn't change, right? The shape can't change to accommodate that. So in this case, you can pick left or right, whichever you like, but there's no magic way to deal with them, right? So for the purpose of the moment, we will simply say, well, we're not dealing with dupes, right? We're pretending they don't exist. And then we'll come back and do some thinking about how to make it smarter in our project. Because I don't like this, actually. This doesn't actually work for me very well, right? For what we want to do with them, we would like to know that when we found the 2, we found the 2s, right? But that's another matter we'll take up. All right, any other questions about that? If it were merely a matter, yes, if it were merely a matter of how many of them, we could add something inside the node that would have more information to say how many. But if you have object references or different kinds of data, that doesn't work, right? Because you need to be able to refer to different objects, not just one object. That's probably, right? So then, you know, it might be that it is somewhat duplicated in terms of the tree, but it has other information that duplicated, so you can't just do that. It's a good idea, right? It's a good start. Okay, but we'll talk about that. Okay, any other questions then about that? Okay, cool. So let's talk about ways that